lines of lies and the lying liars who tell them, I'm going to tell you about this thing, the largest scientific instrument ever built. And surrounding it was some of the largest conspiracy and lies ever told. And it's a story of extremes. It is a story of something very large, something very slow, very powerful, and for a long time, very secret. And today, there's still a lot of secrecy surrounding this topic. And what was this thing? Well, to tell you what it was, we can make some guesses first. So this is ENIAC. It might be a good guess. It's the first Turing computer, consumes 150 kilowatts of electricity, weighs about 50 tons, and had about 5 million hand-soldered joints inside. But it turns out this is actually pretty minuscule on the scale of modern-day instrumentation. This thing I could give an entire talk on. This is called a tunnel boring machine. It's the largest piece of construction equipment ever built. It's over 4 football fields long, and it is able to dig through 40 meters of solid rock a day. And recently, one of these machines completed the largest tunnel ever built in Switzerland through the Swiss Alps, about 35.5 miles long this past March. A common guess that people guess is something like the Fermi accelerator rings at Argonne National Lab in Illinois. Each of these rings is about 7 kilometers, and that's pretty big. That's a pretty big instrument. And of course, the number one most popular guess in modern times is the Large Hadron Collider, which has a 27-kilometer long ring, where it tries to smash things together and, end life on Earth as we know it. I don't personally believe that, but actually all of these guesses are wrong. But to really understand what it is, you have to understand why it was built in the first place. And so our story begins, like many good stories, at multiple points in history. So the year is 1620. This is a dim thing here, but anyway, the year is 1620. A guy by the name of Cornelius Jacob Zoon Drabel has been hired by James I, the King of England, to build a fish boat, which is described as something that kind of can sort of go underwater. It's powered by oars, and for the first time it set sail on the Thames River in London. A few years later, the famous philosopher John Wilkins suggests that such a craft could be used for warfare, but it's not for another 200 years that the French and the Americans combined forces during the Civil War to build the USS Alligator, which is this little craft right here. It's 47 feet long, it's fully submersible, and it's only 4 feet in diameter. So to power this thing, people inside, this is an actual diagram of the inside of the ship, had to sit on little things and crank the ship. And there was no motors, of course, at that time. I think you couldn't steam power it, right? A little bit later, this design never actually worked, but they figured out how to take down ships with it, and then this guy came along. His name is John Henley, and he built the USS Henley. It's the first submarine to sink an enemy ship during the Civil War. The way they did it was they would take an explosive, put it on the end of a long stick, bring the sub up to the surface, reach the explosive out, ignite it, blow up the ship, and then go back down into the water. This submarine sank 3 times, all 3 times killing everyone on board. On the last voyage, he died with it. They lost it on the last voyage, and recently, in 2000, they found the USS Henley off the coast of South Carolina, and it's now in a museum down there. The first modern rendition of a submarine, something that actually had an engine, could stay under for a while, was built by a guy named John Holland. He started a company called General Dynamics. Some of you may have heard of it. It's the 5th largest defense contractor in the world, and they build all of the nuclear submarines for the United States and England. So that is the legacy there. The other point in history that we begin with is it's a brisk July morning in 1945 in the middle of the New Mexican desert. It's approximately, in this picture, 16 milliseconds after the ignition of the first nuclear weapon. That fireball is about 600 feet across and has released some 20 kilotons, 20,000 tons equivalent of TNT. Sends the first mushroom cloud high into the sky. And I guess on a kind of morose note, a few days later, or about 3 weeks later, they used that weapon for the first time on Japan. 64 kilograms of uranium are used, and only 0.7 of a gram actually ignite that 16 kiloton explosion. So less than a gram was actually turned into energy during that usage. Now, let's put these two facts together a little bit. What do you notice about planet Earth? It's approximately 71% covered in water, and every major population center around the world is located on the ocean. So if you want to control Earth from a military standpoint, what you're going to do is you're going to try to design submarines that can attack arbitrarily across the globe. Now, before the advent of the nuclear weapon, back in like the earlier days of World War II, the way a submarine worked was it had a diesel engine on board. You had to surface the submarine. You had to turn on the diesel engines. They would charge a battery, much like a modern-day locomotive works. You turn off the diesel engines, go back under the water, and the batteries would zoom you around until the next time you had to come up when the batteries ran out. This is a modern Vanguard-class submarine. It weighs 18,000 tons. It's 560 feet long. And you can see here in the center a strange set of doors. And we're going to get to what those doors are in a second, but you can probably guess. On board, somewhere on that ship, is a big red button. And that big red button does this. Each of those bay doors holds in it a Trident II nuclear missile. There are 24 on board. And when you hit it, they launch, and they can go 7,000 miles at 13,500 miles an hour. That means they can hit any target in under an hour. That's what one of these missiles actually looks like in a test flight. And to really understand what all this nuclear non-proliferation was about and why the Cold War was such a big deal, let me give you a perspective here. One of these missiles, when launched, goes up into the atmosphere. It carries with it 8 warheads, each one independently targetable to a unique position on the globe. And each one carries 475 kilotons of explosive power. That's 23 times more than either of the bombs in Japan. Each missile carries that. Each submarine has 24 of those missiles, and there are 22 of those submarines cruising around the oceans as we speak. So that's the setting for what's going on here. When they come down, it has this kind of godlike rain of fire. This is an actual test mission. Of course, there's no nuclear explosions following it, but this is what it looks like when those independently targetable warheads land on Earth. And of course, this is the future that they proclaimed. And so what they realized right away was we need to be able to talk with these submarines. And they had set up a whole series of kind of game theory ways of handling this. The US had something called first strike, which meant if times were looking rough, if it seemed that nuclear war was imminent, they would launch all of their weapons at their targets and try to annihilate their enemy before they could respond. That's called first strike. In anticipation of that, the USSR built a different kind of system called the dead hand system. And what that means is that if via seismic measurements, light measurements, and radio broadcasts, or actually the lack thereof, if it detected that the country was annihilated, there were automatic systems in place to launch all of their nuclear weapons at predetermined targets. So this is the problem, is you've got this thing set up where you basically locked in a game theory where you could end the world very quickly. The UK in standard civilized form had a far more clever version, something called a letter of last resort. No, seriously. On each and every submarine, there is a handwritten letter by the prime minister to the captain of that submarine telling the captain, if you can no longer make contact with the homeland, and the assumption is via BBC4 radio transmission that the homeland has been destroyed, that letter contains the information about what they should do in that case. Nobody knows what those letters say because they've never had to open them, and they're always destroyed after each prime minister leaves office. And of course, the idea is to avoid, with all these systems, something like this, the destruction of life as we know it. And what that means that you need to be able to communicate with these submarines with utmost accuracy anywhere on the planet. And at the time, there was no system to do anything like that. So what was this thing that they built? Well, it was, in a word, an antenna. But to call it an antenna like the kind that we put on our houses or something like that wouldn't really be quite accurate. And to understand just how awesome of an antenna it was, we should discuss how it was built. So first, let's consider what's going on here. You're trying to send a signal into the ocean, right? That's where the submarines are sitting. The ocean is a conductor. It's salt water, so salt water is conductive. And there's a phenomena where if you try to send a signal of a high frequency into a conductor, it attenuates. That's a technical term, which just means it gets essentially like muffled, or the signal gets weaker. But if you send a lower frequency, and it'll go a little bit longer. Now, you know this to be true because, for instance, if you've ever lived in like group living or something and your roommate's having sex, all you hear is the muffled groans. You don't really hear all the nice high-pitched stuff. And that's because almost every material that you know of, including sheetrock, water, and whether it's acoustic waves or electromagnetic radiation, they all have the same basic principle at work, that they tend to let lower frequencies through and block higher frequencies. It's just like a natural physical phenomena. And so at the time, you had things like radio waves, which are about 100 million hertz. Like when you turn your radio to 101.1, that's 101.1 megahertz. That's the carrying frequency. Down 10,000 times less than that, at 10 kilohertz, the signal only reaches about 20 meters into the water. Submarines are cruising around at 1,000 meters down. So how do you talk with them? How do you let them know, hey, it's time to launch your weapons, hey, it's not time to launch your weapons? And so they came to the realization that if they were going to be able to communicate with this submarine, they needed to generate a 50 hertz signal. Now, mind you, we were just talking about megahertz, hundreds of megahertz. This is a 50 hertz signal, so it's considerably less. The wavelength associated with that is about 4,000 kilometers long. Earth is only 13,000 kilometers across. Now, what you probably noticed about antennas in general is that they tend to be kind of oddly large. And the reason they're large is because in order to broadcast a signal efficiently, you need to make the antenna roughly the size of the wavelength. And if that seems strange to you, it's because of this phenomenon called resonance, where if you have a ball on a string, on a spring, and you're kind of going at one frequency, you'll notice it'll bounce a little bit, and if you hit just the right frequency, you'll get a very amplified signal. So they had to build an antenna of the right size to get it to work. They also had to build a signal that could be heard everywhere, because as you well know, when you shout or when you turn on a light, any kind of point source of a signal, the strength of that signal tends to decrease like the square of the distance between the receiver and the transmitter. And so before we get into the details, as if these weren't details, and let's look at Earth for a second. How is Earth built? Earth's got a crust, nice and solid. That's where the oceans are. That's where we live. It's got kind of a gooey upper mantle, which is pretty hot. It's got a lower mantle. It's got an outer core, which is basically liquid molten metal. And it's got an inner core, which is essentially solid metal due to all the gravitational pressure that's on it from all the layers above. So around this time, Russia starts a project called the Kola Super Deep Borehole. In 1965, they start drilling into the Kola Peninsula. And some 24 years later, they've only made it 12.3 kilometers. Now, sure, 12.3 kilometers is a ways, but consider it took 24 years to get there. So this is a very slow operation. By the time they'd hit the mantle, it was just this like gooey, hot mess, and they couldn't get through it anymore, so they stopped. And this hole was only the size of a cantaloupe. So what did they do? Well, they realized that the Earth was basically a big resistor. It has lots of metal in it, but it's also not particularly conductive. And they said, well, what if we just build a whole power plant and hook up some electrodes to the ground? So they drilled these holes about 20 to 45 kilometers long, so they went down and then under into the mantle. They were about 50 kilometers apart. They pumped about 1 billion watts of power into it, and they turned the entire mantle of the Earth into a resonant dipole antenna to be able to communicate with the submarines. That antenna output a mere 10 watts of power. So consider you put in 1 billion watts, and you got 10 watts out. 10 watts is about what a good walkie-talkie will put out, for perspective. For a slightly different perspective, the Hoover Dam generates about 2 gigawatts, about twice as much power, using 11,000 cubic meters of water per second, and that would be like harnessing the power from one 100 milliliter beaker of water coming through the dam. So it's not a particularly efficient system. It was also very technologically complex. I mean, not just the drilling operation, not just the building of a power plant, but this was like a complicated piece of electronics. And this is an actual patent diagram for this device in the US Patent Office. You can look it up yourself. And so in the end, only 2 countries had the technical know-how and the resources to do it. You want to take a guess? USSR and the United States. Russia's was called ZEVs. It operated at 82 hertz. The USA's was actually built 2 of them, and they were called the Seafarers, and they operated at 76 hertz. Russia built theirs right where they had done that large hole, and the USS put theirs in Wisconsin and in Michigan. Now, when they turned this thing on for the first time, it became you could pick up the signal anywhere on Earth, right? That was the whole point of the system to begin with. And people started picking up these funny signals and realized that they had structure to them. They were sending messages of some kind. Of course, they were highly encrypted. And these sorts of things started to appear in these sort of conspiracy literature. These quasi-standing scalar this is actually a direct cut and paste from one of these things. I love, if you ever go to conspiracy websites, the amount of bolding and italicizing and underlining is always indicative or in proportion to how erroneous it is. So it says these quasi-standing extremely low frequencies, so these are called ELF waves, humorously enough, that naturally exist in the Earth's electromagnetic cavity, which is the space between the ground and the ionosphere. These Earth brainwaves are identical to the frequency spectrum of our human brainwaves. And they thought, well, how can we prevent the governments of the world from controlling our brain? Well, probably some of you have heard of a thing called a Faraday cage. Maybe you have, maybe you haven't. And it's basically a metal cage that blocks electromagnetic signals. And it was from the turning on of this device that the tinfoil hat conspiracy began. That's where it started, was when they turned this thing on and they started picking up these structured signals, people thought the governments, or these two governments, are trying to control our brains. And this is how the tinfoil hat conspiracy began. Now, in 2004, these systems were shut off, and today, no one knows exactly how they're communicating with the submarines, but presumably there's some other method. A leading contender for the current day communication, at least in the conspiracy crowd, is this little establishment in Gakona, Alaska. It's called the High Frequency Active Auroral Research Program, otherwise known as HARP. Some of you may have heard of that. And so it's basically an antenna that's actually used to study the ionosphere, but if you search HARP, long before you get to the scientific website, you will find hundreds of conspiracy websites about the fact that this is causing earthquakes and controlling weather and all kinds of crap. And so with that, I will finish and say that every conspiracy you've probably ever heard of has some root in truth, but to a large extent, they're entirely bullshit. Thank you.